we're going to be considering supervised learning, so which is part of the machine learning course center framework. So in the previous section, we discussed the different types and some of the application areas that we can subject machine learning to. And the list is actually a kind of non-exhaustive. So the list continue. So, and we'll keep exploring it subject to the availability of opportunities and time. So when we say machine learning, especially we are now going to look at the supervised learning, and it's justified in the previous picture and previous lecture why we have to do that, because this is the common one. Let me say easier to develop, and also can actually get result that you can trust. So because it is supervised, it's like you teaching someone under the supervision of a professional teacher. So, and then finally you subject that kind of student to test. You expect that student, all things being equal, to be better than someone who has not been having such an opportunity. So we always wish that, let me summarize it by saying this is the wish of an average machine learning expert or practitioner. So we always wish that the data they are bringing to us is having label, which is why we call it supervised learning. We have the label to train our data. When we have data without label, that is a little bit challenging. We have to use other algorithms like clustering, which is called unsupervised. In that case, we cannot supervise our learning. We just leave it to the whims of that particular algorithm. So sometimes it comes up with partitioning that might really not be correct. But however, once we have data that is labeled, at least that's a good news for us. Then we keep moving. Is the data, is it clean or not clean? And host of other stuff. Now, so when we talk of supervised learning, we're talking of given the training examples, you'll be given training examples, X1, f of X1, and host of others. This is f of X1 and the output. You are given another sample, and then this is the output of it, up to the last one. This is the input, and this is the output. Now, so for some unknown function, y is equal to f of x. For some unknown function, y is equal to f of x. So we need to find the f of x that can predict the given outputs when we have a totally new testing set, where x is not in the training set. Here, x is here, we are given the value of x. We are given the value of x. We've explained this in the last section. So, but we want to look for an f of x that can generalize. This is called the training process. That once we are done with the training, we can use it to predict value, what is the output of a new sample that was not originally as part of the training set. So we can use it to predict future cases. We use supervised learning to predict future cases. We use it for knowledge extraction. Let's look at a simple illustrated example for it, a simple illustrated supervised learning problem. The problem is, let's say you decide whether to wait for a table at a restaurant based on the following attributes. You decide to go to a restaurant, maybe to have some gathering with your colleagues or with family. So you get to a restaurant, you need to determine maybe should we wait or should we not wait. It looks very simple, but it's a very big issue in some cities where going to restaurants is a big issue. So a simple machine learning is to be developed for this kind of people, that people can log into their system and check on their phone. Should I wait or should I not wait? So these are the attributes. The first step in supervised learning, we need to come up with the attributes that are going to assist us to train the system and also to take decisions. So when we come up with the attribute, you select attributes that are relevant. For example, you want to determine the the strength of a material. So you look for what are the characteristics of that material that can affect the strength of that material. We get those attributes ready and we use it as the input. So you can see here we have alternate. Is there alternative restaurant nearby? So if I get to a restaurant and maybe there's no time for me, it's not yet ready, should I wait or should I not wait? This is what we want to decide. The problem is we need to decide whether to wait or not wait. So this is a classification problem. This is a classification problem, which is one of the supervised learning types. So is there a waiting area that maybe I can wait there to drink tea while they are preparing our sitting table for our own group? Is there the waiting area, maybe that can influence my decision? Is it Friday or Saturday? Are we hungry? If someone is hungry and they say, oh, it's going to take like 2 hours to wait, maybe we better go to another place. How many people are waiting? How many patrons are waiting? None. Some people, full. If this place is full, maybe I might have to start going. So price, what is the price range? Maybe it's costly. If the restaurant is very costly, it's 3 digits, no money, maybe you have to say, oh, I better look for another place. Raining, you can see this another attribute. If it is raining outside, even if you don't like the price, you may not have option but to wait, because you don't want you and your children or your people to get soaked in the rain. You see, these are the ways you see contradictory, opposing attributes are combined together to help us in taking decisions. This is how supervised machine learning works. Now, reservation. Do you have reservation before? Kind of restaurants. Is it French? Is it Italian? Whatever options you have in your locality could be there. Wait estimate. What is the estimated waiting time? When you get to the restaurant, they tell you, oh, we are sorry, there's no space now, but if you can wait for like 10 minutes, if they say I should wait for like 10 minutes, maybe I can decide to wait. But imagine asking me to wait for like 1 hour or more, maybe I'll say, hey, I better go to another restaurant. You see? So these are ways that you can see each of the attributes, they are independent attributes, and they kind of have opposite kind of decision influence to make. Now, the target decision. Target decision is either to wait or not to wait, which is either yes or no. This is our output. This is the why that we want to predict. So when we are done with the attributes, usually we ask the client to provide as many attributes as possible. Don't select it. Sometimes we need to select ourselves. We want machine learning to tell us which attributes are better, because sometimes the thinking of the client is different from what the machine learning is going to determine. This is what we call data mining, and we say that let the data speak. Sometimes you think that 5 out of this is better, maybe machine learning will recognize another one. So always remember, let the data speak. Now, so having got the attribute ready, then we need to gather the data. So it means we go into history. Some restaurants have gotten a lot of customers in the past. This is a sample data set for this problem. Let's look at it together. This is example. This is called, this one is a sample. It's a sample. It represents a person or a group of persons that visited that restaurant that time in the past. Now, this particular customer, number one, there was an alternate restaurant nearby. Remember, that was one of the questions. Is there any alternative restaurant nearby? That can go a long way to influence the decision. Yes, there's alternative. Is there a waiting area that you can wait where they are preparing your room so that you can have a sitting area? Yes, there's no, for this case, there's no sitting area. So you have either you go back to your car or you find your level. Is it on Friday? Not, it's not Friday. Are you hungry? Yes, this guy is really hungry. How many patrons? Some. They are not full, but some. Price is 3 digits money, so it's a little bit costly restaurant. Is it raining? No, it's not raining outside. It means I can easily go out. Reservation. Was there a reservation before? Yes, this guy reserved before. He paid online. You see, he booked ahead of time for that particular restaurant. Which kind of restaurant type, food type, French? Estimated waiting time, 10 minutes, 0 to 10 minutes. Now, what was the decision of this person? He actually decided to wait. We can see. That was in the past. These are customers that came in the past. They recorded their data. They now give us this data now to develop a machine learning system that can always guide the customer on decision to be made. It can also be used by the owner of the restaurant to know which customer will run away after coming and finding that we are full. Can we do something to make sure our customer don't run away because we are full? We found out that when there's no waiting area, they always go. We need to create a waiting area. Sometimes it could be used by the business entity to take more decision to make their customer wait for them. Even if they have to wait for 2 hours, they try to investigate what are the characteristics that make a customer to leave the place. Now, let's look at another customer in the past, another sample, sample 2. You can see there's alternative, so they have alternative way to go. There is no waiting area. It is not a Friday. Hungry? Yes, he's hungry. Full. The place is full, by the way. Very cheap. So we should encourage him to stay ordinarily. It is not raining outside. Reservation? No, no reservation. It's type of food. The waiting time is 30 to 60. Can you see the decision? That customer decided not to wait. You can see now here, if you look at it critically, we try to see what is making X1 to wait and X2 not to wait. This is what machine learning is trying to come up with. What is the relationship between all these attributes and this decision? What is the most important attribute that is affecting the decision of this guy? This one is not waiting. Why this one is waiting? Even though it is a very cheap food, you can see. Let's look at number 3. There's no alternative restaurant near. He cannot go anywhere. Maybe this is the reason he didn't leave, because we found out later that he doesn't leave. He did not leave. You see, because there's no alternative where to go. But you'll be surprised that there are other people where they have alternative, but they did not wait. There's no alternative for this guy. There's no alternative for this guy, but he stay behind. So that's why it's a kind of complicated case that at some point in time, if it's only 2 or 3 data sample, human being can try to solve the problem. But when the data becomes so many, we lost count of how we can analyze it. This is where machine learning comes to play. So when we are given this kind of data, what do? We divide our data into 2 parts. This is called, you partition your data into 2. So let's say this is going to be the training set, and then this is going to be the testing set. So from 1 to 9, I use them for training. I will expose this to the machine learning algorithm, and I'll tell the algorithm that this is true. This guy waits. He waited at that point. I'll give the second one, this guy waited. So the algorithm keeps searching for the hypothesis function. I told us last time, we have hypothesis space H. It picked H1 for this one. Okay, he waited. When you bring the second data, it's not able, H1 is not able to work for the 2 of them. It keeps looking for another H, maybe H7. When you give the third data, H7 work for 1 and 2, but when you bring in the third one, it doesn't work again. So it kept looking for the H hypothesis function that's going to work for all these 9 samples that are used for training. Finally, let's say we got H of 77, H77, which could be an equation, it could be rules. Now we say, okay, this is our model. The final model is generated. It doesn't mean that this one must work for 100%. Maybe out of 9, 7 are correctly predicted after the training for this one. That's good. We can stop if we cannot get something better anymore. Now, having done that, we now go to testing stage. Let's say here we got 17% for training, 70%. Now we now gave this one, these attributes. We give it to that particular hypothesis function H of 77 we have developed. I say, please use this hypothesis function to classify these. We have this customer with these characteristics. Can you tell us, we are going to hide this from our machine. We have it with us. The client will send it to us, but we hide it from our machine. During the testing, we don't expose the result to the machine learning algorithm. We want the algorithm to tell us the result. We now compare the result of the algorithm with the original result given to us. So after running, our algorithm predicted, our hypothesis function predicted that this guy is weighted, but this one does not weight, this one does not weight. It means we got this right, but this was wrong prediction. It means the hypothesis function, out of 3 test cases, it was able to correctly predict 2 out of them, which is not bad, because that's going to be like which percentage out of 2 out of 3. Yeah, that's more than 50%, I think. Yeah, close to maybe 60 something or 70 something percent. Anyway, so this is called supervised learning. So we train the system under the supervision of a label, and then later we use it to make prediction. Now, so that's how we say, given x or f of x of unknown function f, so we are looking for a good approximation for some representation of the inputs. So in this case, x could be contained in this or could be in the real number. Your inputs could be diverse. However, the target function, which is the output, it could be binary classification like the example we just did, which is yes or no. Should they weight or should they not weight? But sometimes it is multi-class problem. You want to predict what is going to be the grade of your student in the exam. It could be A, it could be B, it could be C, it could be D, it could be E. You count them. That's going to be like maybe 7 or 9, depending on the country you are. See, that is called multi-class problem. And it's more complicated compared to binary classification. The more the number of classes, the more the challenge. And then we have here the regression problem, where you want to predict the actual value. I want to predict the final mark of my student in the exam. Is it going to be 3.6? Sorry, 36.7 out of 40 or 37.8? What is going to be the final mark? When you are predicting actual value, we call it regression. And it is more challenging compared to classification. For classification, you can see could be binary or multi-class. Binary is the default. Majority are always binary. If sometimes when we want to solve a problem, if it is multi-class, we divide them into several multiple binary classification. A against B, B against C, C against D, so that we can increase the accuracy of our work. Now, type of supervised learning. Okay, we discussed this already. This is classification, where the output is going to be discrete value, 1, 2, 3, 4, or 5. Was regression, the output of regression is going to be set of real numbers. It could be n number, 3 point something, negative, positive, that's okay. But for this, they are category. Is that yes or no? If it's only 2 classes, or you have 3 classes. For example, I want to predict stock market for a country. Because let me clarify the same problem could have 2 different problem solutions. Like the stock market as an example now, stock market. We can have classification and prediction and regression from it. The classification is, I want to predict if the stock market will go up or will go down. This is classification. But then the same stock market, I can decide to make it regression. I want to predict the value, the market value of that stock price for today. It's going to be 3.6 or 3.7. So from the same problem, the same data given to you, you can have multiple solutions. And that was why I mentioned to us earlier that autonomous driving car has several supervised learning going on, sometimes also clustering. That is, you need to decide, should I wait or not wait? When you have to wait, should I wait at a very high rate of deceleration, brake, or very slow? Should I turn right or turn left? If I turn right, at what angle? So you keep saying classification coming, regression coming. We have problems like that. They need multiple solutions. Now, another example, I say, if we want to predict whether a patient will die from a disease within 6 months, this is called classification. Of course, no one can be actually sure, but doctors do use it to just do estimation. However, if I want to predict how long a patient will live, how long, that is a function of number of weeks, number of days, number of years. That is a regression. So we gave you this example so that we can be able to visualize differences between classification and regression. Also, again, we have this guy already. This is classification, spam or not spam. When you are answering yes or no, it's classification. So we have to take note of that. But when you want to estimate its real number, that is regression. Now, there was a set of activities for us all to do, but because of our time, so the slide will be given to us. You can all practice that. So this is a disease diagnosis problem. The properties of the attributes are going to be the symptoms, the lab test. What we want, the output is going to be, we want to recommend which therapy should we recommend, which therapy should we not recommend. You see, it could be part of speech tagging in an English sentence when you are solving natural language processing. I mentioned to us last time that you can only do good NLP without machine learning these days. Natural language processing is part of AI, but it needs a lot of machine learning work now to really do a serious, so to make a serious solution to a problem. So the part of speech tagging, we want to know when you speak a language, now you have a lot of voice recognition. You want to tell something to say, hey, open the door for me. You know, there are a lot of systems now that can open the door for you. You see, when you speak out, they take the signal from your mouth is converted, then they process it. Where is the verb? Where is the noun? Everything has to be partitioned and treated one by one, one by one. Then they will merge it later. This is called part of speech tagging. It has to recognize when you say, oh, I'm dazed. For someone in another country, a daze is meaning you are surprised. In another country, it could be another thing entirely. So NLP is another area of AI. We are not going into that. So, but machine learning also is being used to support, to solve the problem. So the output for this is going to be, it will output the part of speech of that particular sentence you have. Face recognition, you are given the bitmap image of some people, you want to recognize them. You might need to provide the name or the property or who is this person is. Should he have access to the office or to your house, depending on the kind of security situation. Automatic steering, also you have the picture and videos of the surrounding vehicles and roads. So you want to decide the degree to which to turn the steering. Degree to turn steering is going to be a regression problem because it's number. Turn right 36.3 degrees. But face recognition, you want to tell who is this person. This is going to be classification. And also, this also is going to be classification. This is also going to be classification. Why this is regression. Now, so again, like I said, if we want to predict whether a patient will die from a disease, sometimes when they want to go for surgery, doctor use this, that can a particular patient withstand surgery. They have system that can try to predict and then see, okay, what can we do? Again, this is going to be classification. Why this is going to be regression? Participants should come up with examples in each category. So from your own point of view, try to identify what are the problems in your area that are related to classification, or that you can say it is classification, and which one are regression. So, like I said, because of time limitation, so yeah. So because of a kind of course, time limitation, yeah, still we would like to take, I want participants at this point, 2 participants to raise up their hands quickly and tell me one example of classification in your own area and one example of regression. So raise up your hand. So I will release you to have access to the system so that you can tell us. So we are sorry we won't be able to take more. Okay, Mr. Olayinka Yusuf. I think.
Yeah, thank you. Yeah, am I on, sir?
Okay, yeah.
Naam, Assalamu alaikum, sir.
Alaikum salam.
Yeah, thank you so much for the class. So I am from the agriculture background. I'm a rural sociologist.
Okay.
So, and I work with small farmers. So
Okay.
when I want to give a technology to farmer, and I would want to see whether they will be willing to adopt or not. The willingness to adopt or not will be classification. Whether they'll be willing to adopt or not.
Excellent.
Or whether they'll be willing to obtain a loan or not.
Excellent.
Classification.
Okay.
Yeah. Then if I want to estimate the yield, the yield of a particular crop, the yield in kilogram or in tons that the farmer will get, then that will be regression.
Excellent. Thank you very much. Thank you very much. Yeah, it's correct. I think the second person was Oludayo Afolabi that's raised the hand. Thank you very much. The first speaker, Mr. Oludayo Afolabi, over to you. Yeah, you can unmute yourself now. Unmute yourself and speak.
No, assalamu alaikum. Thank you very much, Professor.
Okay.
I'm from the building background.
Okay.
If I want to determine the class, if I want to put up a class for the air quality in my room, in a particular room, due to the pollutants we have, I think it's an example of classification. That this particular air at this particular room in the same building is polluted by so kind of pollutant. I am classifying the air quality in that type of building.
Okay, excellent.
Now, and if I want to look at the effect of how much a particular home user in a particular building will stay with that pollutant, I think that is regression.
Okay, thank you very much. So you want to estimate how long the people living in that environment can stay without pollutant, without much trouble, or before they recently have chronic disease or chronic issues. That's exactly excellent. Thank you very much. Thank you very much. So because of time, usually I like this kind of interactive section, but we have time limitation. And again, like they have announced actually, for those that are interested in real research or follow up after the lecture, we meet on Saturdays every week, so you can contact Dr. Chijani, the administrator, so that they can actually put you into that particular group if you are interested, so that we can also have opportunity to have regular discussion on this particular machine learning for those that are really interested in following up after the program. Once again, apologies that we cannot take more hands. We can see hands. Maybe another opportunity will come, right? So we need to continue. Thank you very much. Now continue with that. So we have seen how individual, each and every one of us should be able to come up with examples from our area. You can put it up and send it to us later. We can grade you and correct you if you make any mistake. Now, so in supervised learning, we said that we have the discrete, the classification that is clear now. Examples have been given. Why regression is continuous prediction. To do this, we have common consideration. What are the representation? These features you want to use. What features will determine or will assist you to predict or to estimate, like the example given now, the pollutant in the room. What are the attributes of that room that we need to measure easily? And pay attention to this. The attributes are usually easy to measure. You don't want an attribute that is very difficult to measure. But to determine if there is a contaminant or not is challenging. You need experts to come there and do it. But sometimes the experts are not available. Experts cannot be everywhere. So why can't we develop a machine learning system that could be deployed into villages, remote areas to determine contaminant before it actually causes people trouble? So this is where machine learning comes in there. So we have to look at the representation, the feature that can actually support what you want to do. Later, we have feature selection. Sometimes we have so many features, but some of them are better than the other. We treat it under feature selection. Again, feature selection is a whole topic on its own. So for those interested in more detail, we can always refer back to our YouTube channel or our weekly program where we are discuss some of these and some of them will be discussed again. Functional form. The functional form is the hypothesis function I refer to. See, this is the functional form. The h of something that I make the hypothesis function. It could be h1, h2, depending on the hypothesis space we are using. And the evaluation of predictive power. You need to check the predictive power of your model. After you have developed it, you train it, because that's what we are going to know. Maybe there's overfitting or underfitting, as we explained in the morning. Is it overfitting or is it underfitting? That is under the evaluation of predictive power. Evaluation of predictive power is another topic on its own. So that's why we can go into all this. We try to just summarize so that we can have demonstration of how it actually works. Now, on the representation, definition of things to be predicted. Class, for example, classification is classes we want to identify. For regression, we want to know regression variables. So now, but as for instances, the samples that you want to gather, where do we gather sample from? It could be individuals. If I want to develop machine learning model for patients, so I'm going to gather data for individual patients in the hospital. Sometimes I want to predict for family. So I'm going to gather data about each family. That prediction want to identify what is the probability that this family might suffer from a particular challenge. We want to do the prediction. So the data will be gathered on family basis. Sometimes it could be neighborhoods. I want to predict the community where flu might break out very soon or might break out soon. In that case, I'm going to gather data official about neighborhoods and on and on. So whatever you want to model is what is going to determine the kind of feature you are going to bring in. So the choice of descriptors to describe different aspects of instances has to be taken on. Now, formal description quickly. So we say formally, define X as a set of instances described by the features. So given the training example D from X, we're going to take part of X as training set. We call it training example. We call it D. Given a target function C that map X to 0 or 1, this is classification problem, is giving us the output. X is the sample given to us is either yes or no. Is 0 for no, 1 for yes. Now, given hypothesis space H, there's a big hypothesis I told us about. Now we need to determine an hypothesis H, which is small h, in H, such that H of X is equal to C of X. So the idea is for all X in D, we are looking for H inside this big hypothesis space that if we put X inside that H, it can correctly tell me the solution that has been given to me earlier. So when we do that, this is called training. All the training said we want to have H that is correctly identify all the sample. Although I told us earlier, we might not be able to have 100%, but something close to. Out of 100 samples, 90 are correct, 95 correct. These are very good. Now, this is the training. Now, so once we have done that, then the other set, you can bring them in to test the sample. And where we come to an hypothesis that is the most important in machine learning. Everybody needs to know this and know even how to define it. Now, hypothesis space. We said the hypothesis space determines the functional form. Now, you have H. So this is the space. It defines what are the allowable rules function for classification. I say it could be H1, H2, up to Hn, depending on the size. So each classification method uses a different hypothesis space. This is what I want to mention. If you have neural network, it will have its own hypothesis space. You have another one called k-nearest neighbor. It will have another hypothesis space. They don't use the same hypothesis space. So imagine you have H inside this, H in that. That's why I said when you have a data, try different algorithm because you don't know which one is going to work for you. And sometimes we have very difficult problems. the data might not be cooperating, or the problem might be so non-linear and so complex that no single hypothesis space can solve the problem for you. We have that situation. You run the best of false algorithm number 1, you got only 75%. You run B, you got 72. You run C, run as many as possible. They are giving you less than what you want. This is where we come in with ensemble. Why don't we have multiple hypothesis space? You try to understand part of it, then gump together, and you can solve it better. We call it in my local dialect, that is when you, in Unity, actually, you can solve a lot of problems. See, when you have ensemble, you combine different algorithms, they are going to donate their respective hypothesis space. This one got in H2 as the best. This one is saying H3 is the best. This one is saying H7. We say, okay, each and every one of you combine your result and we can achieve 100%. None of them achieve 80%, but we got 100% when we combine them. This is the power of ensemble system. Of course, we can also read more about it, and we can listen to some of our videos where we have actually described ensemble, the advantages, and why you might need it when your algorithm is not able to solve your problem appropriately. However, you should always, first of all, use simple one before you go to complicated ones. Now, inductive learning hypothesis. Inductive learning hypothesis. This is an hypothesis we need to all know how it works. It is the basis of supervised learning. It says that because our data is going to produce by the target, so the hypothesis learned from data in order to explain or predict or model or control. The issue is, it's not just to be able to train. Generalization is very essential. We want a system that can generalize, that can work on data that has not been seen before. That was why I mentioned overfitting. You train on 4 sets of data, you got 100%, but when they brought new data from the industry, the same data set type, but new ones, you couldn't predict it correctly. We said this is overfitting. So inductive learning hypothesis say that if the hypothesis works for enough data, then it will work on new examples. That is, if the hypothesis you have developed, maybe H17, if it works for enough data, the challenge is what is enough data? Let's pay attention to this. Because what is enough for you in mechanical engineering might not be enough in civil engineering. And that is why it's a kind of ambiguous term, and that is the reality. And that's why I say, let the data speak. Let the data speak. I use 20 samples in civil engineering to work for me. It doesn't mean you are going to use 20 samples in mechanical, it will work. It depends on the problem and the nature of the data set. However, hypothesis function says, the inductive learning hypothesis says, if the hypothesis works for enough data, it will work on new example, for sure. And it's like the induction we do in mathematics. You have to prove. Apologies to the mathematician, so we can still remember some of those things. You see, you have to prove that if it works for set of X and whatever, it will work for the remaining ones. We generalize. Actually, that is the principle of machine learning. That if we can have some data set, use it to train a model, train an algorithm to generate a model. If it works fine on that training for enough data, the issue is sometimes you think the data is enough, it might not be enough. In another word, we can state that any hypothesis found to approximate the target function well over a sufficiently large set of training examples will also approximate the target function over unobserved example. That if it works on the data we know now reasonably well, and the data is reasonably sizable, it should work on new samples we are expecting. And this is what we do. We have our client to give us enough data, we divide it into 2 or 3 as the case may be. We use one to build the model, we use another one to test it. If it's going to work, then it will work on this testing set. Otherwise, we need to go back to the drawing board and use another system to check. This is inductive learning hypothesis that governs the principle of supervised learning. So again, it's explained again, mathematicalized. Yeah, like I said, we have so many mathematics. Example of our H could be, like I say, an H could be, this is the X given, theta is the hyperparameter. This is the hyperparameter that you need to set in your algorithm. So it could be as simple as this. Whenever you have a new X, just put it here, plus some weights that have been determined during training, and then you get your result. That could be the hypothesis function, by the way. And it could be this kind of equation, x1 or x2 and x3 or not x4, where x1, x2, x3, x4, these are the attributes that you use in your training. It means with this one, I can always predict new system. And some of them can be complicated rules. And some of them, none of this single algorithm will work. We have to combine several algorithms in what we call ensemble techniques. So the supervised machine learning framework, it's like you apply a prediction function to a feature representation of the image to get the desired output. So I have trained my system. I know this is apple. You can see when I put it in this F, I know this is an apple. I know this is tomato. Then I generate appropriate model so that later when I have an apple, the system could be able to recognize for me that this is an apple, this is tomato, or this is cow. Now, to a layman, I used to say this is how you should explain machine learning to a layman. You see, machine learning is given that y is equal to f of x. Output, prediction. This is the output, what we want to have. There's a function, prediction function. Don't call it ordinary function. You call it prediction function or hypothesis function. Hypothesis function. And this is the feature. It can be image feature. It could be any type of feature. It doesn't have to be image. Now, during the training, so this is the simplified way people can easily remember, hopefully, inshallah, y is equal to f of x. During the training, we know y. This is known. X is known during training. So you'll be given the target, which is good. This is the label. Yx is also known, the output attribute. However, f is not known. So during training, we want to find out what is the f, the prediction function or hypothesis function. However, during testing, we still have the same y is equal to f of x, but this time around, this x is a new x. See, different from this x, new, the one that we have never used before. Now, we know the x will always be given to us. F is already known from this finding of training. So y is unknown. So we don't know why. This is supervised learning at a short. During training, you know x and y, which means you know the input and you are given the output. You want the system to generate a program for you, which is a hypothesis function. Then you use that program for prediction in the testing stage. Doing that, you solve what we call the supervised machine learning framework. So that's what we have explained there. Given the training set, you use the F that you calculate to compute the new output that is not known. So again, once again, we saw this before, just to remind us. You see, so these are the images. You extract the features. While the training is going on, you keep labeling them. This is an apple that we're teaching a baby in the school. This is an apple. This is a mango. You keep doing that for your machine learning algorithm. Keep giving the label. Once it's learned the model, now use that model for prediction here. Here, there's no more A for apple anymore. You want it to do the job by itself. This is training and testing. Now, this is what I call the generic machine learning framework. So the generalized pattern you need to follow. The first is start. This is small flow chart. Data gathering. You need to prepare your data, like we are going to see now. We are going to demonstrate for us. So we are going to demonstrate for us how we can have this done. So you gather your data, then you try to pre-process the data. This is optional, by the way, but gathering data is compulsory. Gathering data is compulsory. Lazim. It's compulsory. It's compulsory to gather the data. Then you prepare your data, you put in Excel, whatever you want to put it. Then we have the data preprocessing. Sometimes this is optional. Your data is good. There's no missing value there. There's no outlier. Everything looks good. Then you are good to go. You go to model building. You select your algorithm. Is it k-nearest neighbor we want to talk about? Is it KNN you want to use? Or neural network that we want to use? Select the algorithm. Now you divide the data into two. You have the model building. During the model building, it's a very big procedure, by the way. This is the training. Okay, this is training. You see, once you train, then you need to test. You test it. You check that the training I've done, is it working fine? You check here, there's a kind of a flow chart. Need to refine model. Yes, it means your model is not good enough. You go back. There's a loop here. Parameter tuning. You can change the parameter of the algorithm. You go up again. You rebuild it. You can see we didn't go to testing. We go back to building it. Train again. Is it working fine? No. You keep going for need to refine model. Yes, we need to refine model. You might need to make your own to be, is it working fine? Yes or no? It's flexible. You keep doing that until need to refine model. No, I think it's fine. I already got 98% accuracy in training and 97% accuracy in testing. And we have tried, it doesn't work. It's okay for us. Our client said they needed 95. We got 97. That's okay. We can stop. Then you build the final model using the parameters obtained. So using all the parameters you have searched for, all the procedure you have checked, you build the final model. This is here, we call it data preparation, step 1. Step 2, we call it the learning from data. You are learning from data. This is learning. This is learning from data. See, this is where we let the data speak to us. And then final step, we have carrying out prediction and interpretation. This is where now model validation, you get another data from your client to check again that what you have tested before is still working, is still correct. You see, sometimes you develop a model, something went wrong. You don't want to deploy a system that is not perfectly okay or not working to your client. So that's why we need to validate again. So you get another data. Sometimes when they give us the data, if the data is sizable, we divide into 3. We divide into training, testing, and validation. We keep them separately. We use first one for training, second for testing, and the third one later we use for validation, just to be sure the system is working. And then prediction using the model, you can now deploy it to your company or your client. Let them test it if it's working. Is it doing what they want it to do? Then result analysis, analyze your results, interpret your results, and what are the identification of hotspots? See, you need to identify, that is the analytics part of it. You need to analyze what you have gotten. Could we have made it better? Is there anything we can do to make it better? Can we do it using another algorithm? Why can't we use combination of many algorithms, what we call ensemble? All those kind of questions. For researchers, we call it fencing, fence in, and fence out. Fence in, those things you have considered in your research, you have done them. But as researches are going on, ideas will be coming to your head. You cannot do everything. You have to fence out some. They are relevant to your work, but you cannot do everything because research has a time ban. So next time you are going to identify the hotspot, future work to be done, and then recommendation. This is a kind of, I call it a generative supervised machine learning framework. And I think that's it about supervised learning generally. So there are so many other things we can actually mention, but because of our time, we need to go to look at example of algorithms. See, we've mentioned algorithms. So this AI is trying to tell us, for example, you want to class of a family car, you want to predict, is a car a family car? You want to solve that problem. You want to predict if a car is a family car or not a family car. Then we have knowledge extraction. What do people expect from a family car? This is how you build your features. You see, the output is either positive or negative. Is it a family car or not a family car? Example of input you can get is price. What is the price and what is the engine power? For a family car, you need a very big engine. So this is a kind of input that you can use to develop a system that can predict if a car or identify if a car is a family car or not a family car. Somebody say, how do we know this? Or when do we need it? Depend on the problem and the situation report. So this is a mathematicalizing the classification. You have the hypothesis class H. So we have to say the hypothesis function H is going to be defined as 1 if H is positive and 0 if otherwise. In between then you have some mistake that is allowed. We have the false negative and the false positive. So, but because of time, like I said, we won't be able to go into some of these details, but we can always hopefully synchronize later when we have the opportunity to even make it more details. So we're going to have the H that is contained H between S and G. We have misclassification error that is possible. We have false positive and false negative. False positive means something is supposed to be negative, but it's classified as positive. False negative is something is supposed to be negative. Sorry, it's supposed to be positive, but it's classified as negative. Like you develop a machine learning system for predicting patient status. You say somebody is sick, meanwhile it's not sick. That is false positive. But you say someone is not sick, meanwhile he or she is sick. That is false negative. So you have this kind of, you cater for this kind of mistake. We are not always expecting 100% accuracy. For regression, got that one from the popular statistical regression, something stays similar. So you have the point we are targeting. These are the targeted points. So can we really train a system that can identify all our points or closer to the point as much as possible? So in that case, we are going to give room for error. There's going to be an error that we are going to calculate the error. What is the difference between the predicted value and the actual value? You can sum them together and then divide it by. This is going to give us the error of estimation for the regression. It could be root mean square error, it could be absolute error, and so many other errors. How do we determine which kind of performance measure we are going to use? You have to check the area you are working. This is very important. You see, each area has set of performance measure. If you're working on classification in civil engineering, check previous paper in that area. Except you are the first one to work in that area, then you can consult experts to guide you on what is the best performance measure to use. If you are working on regression also, you consult earlier work and then try to see what you can do in similar way. Otherwise, consult experts also to be able to guide. So, and then on feature extraction, do we have the raw pixel? Sometimes your feature extraction could be as simple as raw pixel that you are going to convert it into histogram or use histogram or GIS descriptor, depending on the kind of problem you are solving. And then we go to example of classifier, and the one we are going to consider is going to be nearest neighbor, because the idea of classification is we want to develop a system that can recognize. We have two class problem. Can you tell me, is it class blue class or red class? How can we know that you belong here or you don't belong here? So this is where we need an algorithm to do that. So, and that's why shortly, so we want to see, can we find a linear function to separate these classes? We know there are two classes, but how do we separate them? What can we do to separate them? So we need an algorithm to be able to do that in machine learning. And finally, before we go to the algorithms, there are many machine learning algorithms to choose from. We have support vector machine. We have support vector machine. We have neural networks. We have naive-bayes. We have Bayesian network. The list continues, by the way. So k-nearest neighbor is going to be our friend for the day. We are going to look into k-nearest neighbor because it's very easy to understand as for beginners. And then others also, they're all very interesting. Depending on time, we're going to see how much we can cover. As many as these classification algorithms are, which is the best one? No one can really tell. And I want to reveal something to you. Whenever you see somebody telling you the best algorithm is this, that person doesn't really understand the basic fundamentals of machine learning. You don't have best algorithms. It depends on the data. Again, I remind us, let the data speak. See, you can have algorithm, super vector machine used to work for me and my team very much. We use it a lot of problem solving. But we have used it in a problem that it doesn't work. In fact, k-nearest neighbor work better than it in one case or some cases. So you don't have best algorithms, but rather, so you have to check which one is going to work for your case. And finally, we have the no free lunch principle, that machine learning algorithms are tools, not dogmas. The meaning is that machine learning algorithms, they are tools, they can fail. They are not dogma. Dogmas are things that are fixed, things you cannot change. Mobeni is permanently made. You can't change them. Some principles like that in life. But machine learning, no, it's ordinary tools. Sometimes it works, sometimes it doesn't work. And there's no really free lunch. You can look at here. There's free lunch here, but you need to pay $10 to enter. How many dollars are you going to use to eat? So when next time somebody tells you something is there, so you have to check, actually, is it really the case? The idea is that no classifier is inherently better than any other. You need to make assumptions to generalize. And then try simple classifier first. And that's why we're going to start with k-nearest neighbor. And then you move to complicated one as the problem also become complicated, until you have to start thinking of mixing them together in what we call mushakel in Arabic. That is a kind of cocktail. Sometimes you might have to have a cocktail of algorithm. Imagine having a problem solving that has like 16 algorithms with 275 models or even more, because you want to get maximum result possible. This is ensemble. And that's the latest area people are exploring because of the potential of getting better results than individual ones. It is better to have small features. Let's pay attention to this. Better to have smart features and simple classifier than simple features and smart classifiers. I'll try to explain what I mean. You see, better to have smart feature. Your data is very important. Again, they say, I used to say this word very well, too much. Let the data speak. If your data is good, even a very simple classifier will solve your problem for you. This is the meaning of this. It's better to have a smart feature because features will form your data. If you choose wrong feature, you want to predict the student that is going to fail an exam or not. You started asking for which food did they eat their family. What does that have to do if he's going to pass exam or not? So you are choosing the wrong feature. So your feature is not smart. We have to ask questions that are closer to what we want to establish. Does he come to class? How many absenteeism does he have? Does he write in exam in class? Does he contribute in class? Does he fail prerequisite course? You are asking related questions that can determine if a student will fail or pass. This is what we mean by smart features. You have expert to kind of get some smart feature, but at the same time, sometimes it's good to have, just bring the data, don't send them away. Machine learning will assist you sometimes to select the best features. That's why we have another big topic on that, feature selection. How do you select the best feature in the midst of several features that are available? That's another way we do that. There are several attributes, several types of methods to do that. So it's better to have smart feature and simple classifier than simple feature and smart classifier. That is, you have very bad data and you say, yes, I trust my algorithm. No, there's nothing like that. The best of algorithm will not perform in the presence of very bad feature because the features are not related to the problem you are solving. So this is what we have to take notes and also use increasingly powerful classifiers with more training data. Always, as your data set is getting more, then you need to increase the power of your algorithm. So if data is small, you can use simple. As the data become more, the complication get into the system and you go for more higher classifier as the case may be. And then finally, classification versus regression. I think we have discussed this a lot, that we should be able to understand what is the difference between classification and regression.